Hello, hello, Rishikesh. How are you doing? Do you hear me? Okay, I think I will start. Share my screen. Yes, so I will start here. We were discussing how, given two BDDs, we could apply an operation. We could construct the result of a BDD for the result of applying a binary operation, logical connected, on the two functions represented by the two BDDs. So this is the algorithm that we used. I'm going to go through the, on an example, the one that I did not go through and I asked you to simulate. Do you have any questions before I simulate this thing on an example, just to see how, with the data structures that I introduced, that the new BDD for the result of applying these two operations is going to get constructed. Before that, do you have any questions on BDDs per se, or the data structure that we used for these things, and the primitives and the make functions? Any questions? Okay. So this is the example I'm using. So this BDD on the left represents the function x1 if and only if x2. The one on the right represents the negation of x2. And as you can see, both these are considered as functions over two variables, x1 and x2. x1 does not appear in this BDD at all. Why? Can anyone answer me that question?
The result of like the final result of the function does not depend on x1 at all. So
That's correct. See, that is unique for a BDD or ITE canonical form. That's not true of CNF and DNF. Okay, you could still have the variables in there, in the formula, in the expression representing that, and it's only because of this reduced property. Okay, that's an observation that I wanted to make. I hope you realize that, because of the elimination of the redundant
The
nodes.
fact that reduced probability are unique, right?
Uh, well, even without that, given a variable as a particular variable ordering, it is still unique. Okay, it would still be unique, but this compactness is guaranteed. That's the reason for using this redundant node elimination. And it's the result of applying the redundant node reduction that gives the ROBDD this property. Okay? Does that answer your question?
Yes, yes.
Okay. What you should observe, and the reason I'm going through this is because when BDDs are used, each node each node in a BDD represents a unique Boolean function. And also the construction process is such that for every function that you have constructed so far, for every Boolean function, there is a unique node in the repository of the BDDs that you construct representing that function, okay? So you will never, unless you explicitly discard a BDD that has been constructed, there'll always be a unique ID, a node in your table of nodes that I introduced in the data structure, at which that function will be there, okay? And I mean, you can always query your data structure to see if, given a variable with a particular BDD as its low argument and a particular BDD as its high argument, if it already exists, if you've already constructed, okay? And that is also something that you will have to keep in mind. Okay? And that is illustrated in this algorithm as well. Although I've shown this that's why you see the right side argument is actually not there in the data structure that it uses in the table. The node 4, which has whose variable is x2, is actually there although I've shown two separate copy of those things in the data structure, it is represented by the same node 4. So you start with applying the OR. I guess in this case it's the OR operation that we're doing, the plus operation here. So you start with the BDDs represented by the node 5 and 4. So you get the variable of the node stored at 5, which is variable 1, representing x1. And the one at 4 is x2. And since the ordering is, as shown here, x1 is less than x2, you take the entire second argument and do, so you apply it, the function, the R function, to the low side of BDD 5 and high side of BDD 5. Okay, so the result of making a new BDD out of it. Okay? And for that, the make function is used. As I had shown you in the last class, the make function does all the checks that are needed to see if the once you have got the BDD for the first argument of make and the right side of the argument, you can do a check to see before it constructs a new node if that there is a BDD already for that function that you would be constructing as a result of that. So in this case, what will happen is that will happen only when you return from the recursive call. So now you recurse down to evaluate app of low 5, 4 and app of high 5, 4. That then will result, okay, so this app will result in a low of 5 is, so where var of 5 is 1, x1, so this simplifies to x1, and app low of 5, low of 5 is 4, unique ID 4, therefore this is app 4, and high of 5 is the BDD stored at node 3. Therefore, you get app 4 and app 3.4. Okay, that's what this simplifies to. And app 4.4 results in the following. So 4.4 means, so you will have a recursive, in the recursive call, you will check the var of 4 is the same as the var of these two nodes are the same because they're identical nodes. So you have, and that's 2, and therefore you will do, then you will apply, do an apply on the 2 low sides and the 2 high sides, okay? So, and that is the low side, the high side of 4 is 0, and the low side is 1. So it's an app on 1, 1 and app 0, 0. That is the base case for the app function. Therefore, this results in 1, and the second argument results in 0. So that means that you have to make 4, 2, 1, 0. And you see, make of 2, 1, 0 is already there. So make actually checks if, given a variable 2 and a low represented by the unique ID 1 and 0 is already there in your table. And that, so since it is there already, it's exactly identical to the x2, not of x2, which is what the BDD at 4 represents. So it's already there, therefore, it doesn't create it afresh, it just gives the unique ID of 4. So that's what preserves the uniqueness of, for any function that you be created only once in your BDD. So app 3.4, is also app 3.4, but there also the variables are the same, you see, var3 and var4. That is, the var stored there is x2. And therefore, you do the same thing as this. So you do the ORing of the 2 low sides, ORing of the 2 right sides, and that will be make 2, 1, 1. What is that? Make 2, 1, 1 is actually 1, the node 1, because both sides are the constant 1. Therefore, that gets 1. Okay. So 1 is also already there. So that's the BDD corresponding to 1. And that's why this whole thing here in red, the original make function gets simplified to 1, 4, 1. And that's a new node that is not there in the, that has not been constructed. So that makes a new node. And that's what is 6, okay, which stores the variable 1, and the low side is 1 and the high side is 4, which is exactly what is constructed. Okay, so that is the final result. And so the make, as a result of this make here, it creates a new entry into the node table. And of course, the reverse table is also accordingly updated. So you have this new node as the thing. So 3 and 5 are the original one, which are not referred to by this result, but they might as well still be there if you wish them to be. But for the second argument, the BDD represented by at unique ID 4 is still used, okay, as since it is part of the new result. And that's how it is. It's done. This caching part is what is very important to realize that, to have this, to make all these BDDs work. And that's what I wanted to make sure that you understood by going through the algorithm. Any questions? Okay. Yeah, as you can see, this whole thing is linear in the total size of the two BDDs. Linear, yeah, so it's the linear time algorithm, okay? And you should remember, most BDD operations are linear in the linear time and the size of the argument BDDs, okay? But what might happen is that the result of the BDD for the result function, the resulting function may not have a compact representation, in which case the output, the space, that is required to represent the result can be exponential. Okay, that can happen. Here is another important operation on BDDs that you will need for doing the existential elimination operation. This is restrict operation. So this operation, given a BDD for a function of three variables, x1, x2, and x3, that is represented here on the left side, which denotes the function given by the expression on the right-hand side of the equation here. You want to construct a BDD which represents the restriction of this function by restricting the second argument x2 to 0. Or, things like you may want to restrict the first argument. So here the step is very simple. It's all manipulation on these things. So you identify the, so you go down the chain and look for nodes that are associated with variable x. That particular variable. In this case, in the first case, it is x2. Here there are two nodes that store variable x2. And that is now restricted to 0, to be restricted to 0. So all you do is all the incoming edges to these nodes, there are two incoming edges, you direct them to the node that is the successor of the 0 side. That's it. So you just make this dashed arrow go down. You of course get rid of x2, but you just make the incoming edge coming into this follow the 0. Similarly here, this incoming edge, the solid one, you make it go to x3. Okay, that solid edge as is will go to x3, which is the 0 side of this x2. And that is the result. I haven't shown the result BDD for that, and that's all that you will have to do. And yeah. So and as you can see that, and you can work this thing out and see, make sure, convince yourself that the resulting BDD that you get by doing this manipulation on the graph indeed represents the restriction function, the result of restricting the thing. Because the one side is completely eliminated here. The x2 is eliminated on the one side, and therefore, because this is supposed to just use the function represented by the one that is rooted x2 for the case of 0. So, and that's why you direct that towards the successor of the 0 edge of x2. Is that clear? Okay. I don't have the result. I wish I had the result thing. I don't think I have, so if you have any questions when you do that, please let me know. So then, say, as you might have guessed, the existential quantification, that is the result of performing an existential quantification elimination on a variable on a BDD, can be done by by invoking two restrict operations for the variable that needs to be eliminated. One, by restricting that variable to 1 in the function, and 0, and then doing apply of the OR function, ORing those two BDDs. Okay. Of course, you could do better than this, by actually hard coding this thing. I mean, here you're doing actually three traversals of the BDDs, one for restricting to 1, one for restricting to 0, and then doing apply. And that maybe you could do simultaneously. So there is a, and also you can extend that to simultaneous instead of eliminating one variable at a time. You can actually simultaneously, as you go down as you traverse the graph corresponding to F, you can keep the entire set of variables that need to be eliminated existentially. And as you do it, you can simultaneously eliminate them, because after all, you encounter these variables in a particular order. So you could do this restriction and the application so for all the variables simultaneously, and that would be more efficient, and in the sense that it will take fewer traversals. Okay? Each traversal is only linear in the size of the BDD, but yet so by doing this, you will by combining them into one traversal, simultaneous traversal, and resulting manipulation, you can save the number of traversals that you need. Okay. Actually, the book has, it's repeated anyway. Yeah, has that, it shows that function. Let me show you that. Yeah. This is the subject of chapter 8. BDDs are the subject of chapter 8 in the reference book. So I have taken the liberty to reproduce that function. So this is simultaneous elimination of edges. He doesn't use the make routine here. Okay? So you can try and get a make version of it as an exercise, and that's why he uses the caching here. Okay, so the caching and checking if the result is actually in the cache as constructs is done separately, but nonetheless, what's being done is it takes the top variable of F, top variable of G, and then first constructs the restrictions of of that, and then restrictions of that. If Z belongs to E, then you do the OR. Otherwise, you put them, then you just put them back and then go down the path. Okay. So I think this is slightly different than what you see, but as an exercise, it would be useful for you to do this simultaneous elimination of existential variables as you do the restriction simultaneously for a whole list of variables. Okay. Yeah, so that is all I wanted to say about this thing. So any questions you have? Okay, so yes, see, even though so you can go through this thing at your own leisure, right? So and although you might, not have understood all the details of this algorithm, I mean, you're doing it simultaneously, that's all. So if you could think through this, you can get it. But so here, see, what is it that you will have to do? So see, all here, when you eliminate existential, whether it's simultaneously or individually, here you're doing it simultaneously. The expectation is that you have, oh, I'm sorry, this is not the one that I wanted. No, this is something more. Sorry, I rushed through it and I didn't realize the thing. So let me make the point. Okay, so when you do, so I want to take you back a little bit to how a transition relation looks like. Okay. See, all these operations that I've showed you is, yeah. Okay, so I think the point I was trying to make, I'll remake it here. I don't think this is the picture that I wanted. This is doing a little bit more something else. Okay, so which I have to talk a little bit more of here. Okay, so how does our okay, when do we need to use existential quantification over what? Okay, when do we need to use existential quantification? Just to see if you're all awake and listening. So let me ask that question. So when do we, in our model checking, CTL model checking context, when do we use existential quantification in that algorithm, the CTL model checking? When do we use the existential variable elimination operation? Anybody? Hello? Oh. I'm a bit surprised that you can't answer that. Do you remember EX? So in CTL model checking, what is the basic step that is done in the fixed point computation? It's EX, right? Are you guys there? Can any of you unmute and say yes or no?
Yeah.
Okay, so what does EX do? So there is a pre-image computation, correct?
Right.
How is that pre-image done? Using existential, correct? What is that EX? What does the two function that it uses? What is the two BDDs that EX uses? You usually do with respect to, there are two functions, Boolean functions, over which when you do EX, that existential thing does the formula over which the existential elimination is done. It has a predicate, a post predicate, a P. When you do an EX of P, there is a predicate corresponding to P. So that is one BDD. Okay? The other one will be your relational, transition relation. And you'll take the conjunction of the transition relation and the and your predicate, okay? And that will be like R V V prime and P of V prime, which is the predicate that you have to, when if you're doing EX of P, so you will do that, and then you will eliminate the V prime, okay? That's what you do. So the BDDs, that the two BDDs that you will be using them on will be this R representing the transition relation and the predicate, P. That's what will be given in the place of F. Okay? That for which the existential operation, as I showed you, that used restrict and the apply does. But the R itself. So if you were doing it in the previous way by using restrict and applying of R, you need to construct the BDD for what the formula that has a monolithic entity. As you know, R itself, usually we construct in a modular fashion by composing the piecewise relation to each of the components that are composed either synchronously or asynchronously. Okay, so I'm going into the structure of how the transition relation looks like if you were to be using synchronous or asynchronous composition. Okay, and so rather than doing the one way to do is to construct this transition relation by taking the individual BDDs for each of the component module, applying and the conjunction of all the things, constructing a monolithic transition relation, and then eliminating individually, repeatedly these ways. That is one thing that you can do. The question that I'm raising is often what happens is that this process of, okay, for the synchronous case it will be and, for the asynchronous case it will be or, that I will get to. So I'm, just think. So the idea of this, an optimization to do this, okay? So doing and, etc. is thing. It's the existential quantification because of how frequently you do it, number one. And number two, because you're taking the or whenever you do it, there can be an explosion in the size of the resulting BDD. Therefore, so the idea is, so the question that I'm raising is, can you actually do the elimination of the existential quantification without actually constructing the R, okay? That is, can you individually, the hope is that these individual R1 through Rn might be smaller than what you get by taking the conjunction of these operations and then taking doing the operation of existential quantification over R. Okay? Instead, can you do it without? That is the question that I'm raising. If you could do without actually constructing this combined transition relation, that if you could individually eliminate the existential quantification over the individual pieces of transition relation, maybe you can do better. And that is what I'm saying. This is one of the optimizations that has takes significant impact on the efficiency, and that's why and bring this. This method of doing it is called partition transition relations. Instead of taking the monolithic version of R, I keep the transition relation, the composed transition relation, as a list of individual transition relations, and then try and do this existential quantification on the individual things. Okay, that is the idea behind performing this on a partitioned transition relation. Okay, furthermore, each Ri in the case of synchronous looks like this. Okay, where there is a function. I mean, the new value for each of the bits here, V bar and V bar prime. The bar here is not complementation, but rather it represents a whole, a tuple of bits, okay, a bit vector there. So individual bits of this is the new value, the prime value is given as a function of the original thing. So that's the form it takes, okay, of a transition relation, okay. So the reason we have to get into this structure of this is because the method of existential quantification elimination using partition transition relation exploits this structure. Okay. For asynchronous, the structure is there is a disjunction, okay, of the individual transition relation where an Ri, each disjunct in that is takes the form of this. Okay, so you assign one, the one that the new value as assigned by the process Ri, and the rest of the things that the process I doesn't modify remains the same. This is how it is. In the synchronous case, you take a conjunction. In the asynchronous case, you take a disjunction. Okay? Given that, this is what, okay, the basic step in the CTL model checking involves. So it does, you have to take the predicate H, conjoin that, so yeah. Yeah, so if you actually want to do, I'm sorry, this should be R here, not well, okay. For the asynchronous case, let's look at the asynchronous case. You want to do this operation not on R, but not on Ri, but on the entire R, okay, for the asynchronous case. For the asynchronous case, the disjunctive partitioning, there is a mistake here, Ri should be R. Because existential quantification distributes over R, so you can express this whole thing as, you can distribute the existential quantification over the individual R's, and you can actually express it like this. And by distributing moving the existential quantification inwards, and you can actually do it. You can, rather than constructing the R by taking the disjunction, you can do the existential elimination individually on R1. And this might be better than constructing that one because you are, especially if the individual transition relation is smaller and the result of doing this disjunction itself doesn't blow up. That is the idea. So for the asynchronous case, it is because it uses the disjunction, it is easy to do it. Now you can further simplify that because, and then one part of this conjunction just says is equating variables. You can actually eliminate that, and then you will get something like this. This just consists of substituting. I mean, this propagating this equality over these variables, individual variables within H, and this is what you get. Okay, and yeah, but it's still hopefully smaller because Ri is this, and so you can do it. So the asynchronous case, there isn't much work that you need to do, because you can exploit the fact that existential quantification distributes over disjuncts, and you can compute the basic step in the CTL model checking in a partitioned way. Okay, so that is the idea. So using partitioning over the transition relation. Okay. Question is, can you do this also for the synchronous case? Can you? That's a question. Does anyone have an answer? Yes or no? Is this distribution clear? The motivation and why I'm doing this, is that clear? Yes?
Why will this be faster?
Why what? Repeat the question.
So why is this? Why is distributing the existential quantifier over the
Better?
disjunctions? Yeah.
Yeah, well, the hope is this ORing will give you a big PDD. Okay, you can never tell. Okay, so the hope is this individual things will be smaller. So you don't. Yeah, I mean, you firstly, okay, by once you eliminate these things, certainly eliminating our individual things, so you don't need to construct the combined transition relation, okay? Because if that process itself has a blow up, you don't need to construct. See, if eventually, if the function that you get after eliminating the thing, that function itself is such that it is too big, you're doomed, okay? I mean, there's nothing that you can do. So here the hope is that maybe the result of eliminating this thing might be small, okay? That depends on the image, etc. And but just the so you are eliminating the step of constructing the combined monolithic transition relation, okay? And when you take the disjunction here, each of these things, maybe because of the elimination, because that takes the restriction thing, maybe it is hopefully smaller. That is the idea, okay? That is the motivation, yeah. So it eliminates.
So each of the RIs are like much smaller. Is the
That is right. That is the thing. Our eyes are, hope is, yes, smaller, okay? And especially after, so you are doing the elimination of quantification over smaller things. That is one, okay? And then you are, when you eliminate, maybe it will be smaller and a smaller thing, and then when you do the disjunction, it is smaller, because certainly there will be fewer variables in these things, okay? And yeah, so that is the hope, okay? And in practice, this doing existential quantification over partition transition relation seem to work better also, okay? So that is borne by empirical result, and the intuition is that, yeah. So let me get back to my original question. Is can you do it the same way for synchronous? If not, why not? Hint, existential quantification, I'll give you the answer. Existential quantification does not distribute. The step that I made from going, this is R, once again, I remind you. So R is a disjunction. Therefore, I, move H and then conjoin with each of them. And then I'm taking using the rule that existential distributes over R. Because you can't do the same thing here, because existential quantification does not distribute over conjunction, okay? So you just existentially over R, where R is a conjunction of smaller relation, is not equivalent to doing existential quantification over over individual R's. Okay, because existential quantifier does not distribute over and. Yeah, I had, yes. Where do I have something that, okay, maybe if that is not clear, then I had, so is that, yeah, so I also had something where, no, not this, not this. Yeah, these things are what I had here, okay, in detail, but I thought I'll just not go through those slides. Yes, so for example, for the asynchronous case, it's easy because these things do. For the synchronous case, you do not have, you do not have this, yeah, you can't have this distribution over R. Therefore, the best thing that you can hope for is something like this, okay? Which is what, if, so you can't individually distribute the whole thing. But if the transition relation has the individual things as such that usually everything is not dependent on on all the variables, okay? So, yeah, so here the T, the global transition relation consists of two components, and the second component is dependent only on some set of subset of variables. The first component is on both. In that case, you can actually do something like this, okay? So, you know, so this one, there exists an x1, x2, t1, x1, and tn, x2. You can't directly distribute this over individual things, but you can do something like this, because when you you know, split it into equivalent thing x1 or x2, so you get this. This is equivalent to the second step, okay? And then you individually, when you take it, since x2 doesn't appear in t2 at all, and that's not dependent, therefore then you know, you can move some sub-formula outside the scope of x2, okay? And then eliminate x2, just, okay, I moved t2 x1 outside the scope of x2, and I have eliminated x2 from x2 from t1 x2, so that is this. And now this is the same as e of x2. So you can distribute, you can move, you can't completely distribute them over the conjunction, but you can move some sub-formulas that are not dependent on you know, some of the quantified, you know, if it is not dependent, if it's only dependent on a subset of the formulas, then you can move that out, okay? And you can do the quantification elimination in a certain order, such that, like it is here, first do it on x1 and then do it on x2, so that, you know, when you do the second one, you get a smaller formula after having eliminated this. That is the idea. You know, for synchronous, you have, you know, the idea is to kind of look at the set of variables that each of the individual component transition relation is dependent on, and if it is dependent only on a subset, then we might be able to move it by this equivalence that I've shown here, and take advantage of the fact that you do it in some order. Okay, and if you can figure that order out efficiently, then by looking at these dependence of individual functions over the variables, you might be able to do. So that is what the idea. So let me go back to this the original thing that I was doing. Yeah. So take a look at this example. This is the mod. This is a mod 8 counter. It's actually in the book. It's similar to the mod 3 counter. So here, the transition relation is described as follows. Okay, it can come. Yes, because there's 3 components, each of which defines the new value for one of the bits of the 3-bit counter. And you can see that this one, the first prime variable is only yes. Okay, they are all completely independent of each other. Therefore, so an optimal order of quantifier elimination. Here in this case, because you are eliminating the primed variables. So here they all are. R0 is only dependent on V0 prime. R1 is only dependent on V1 prime. R2 is also only dependent on V2 prime. Therefore, you can actually do this in any order. In the sense, you can do it, for example, this way. Okay. So first eliminate V0 prime from R0, V1 prime from this one, and V2 prime, from this thing. You can actually do it in any order as far as long as there's no dependency of these R0. Each of them is dependent on a exclusive set of things. But although from a primed variable point of view, you can do it in any order, this particular order, when compared to the, is even better than the other one, because, so as far as primed variables, you can eliminate one at a time, okay? Because by analyzing the dependency of R0 only on V0 prime, R1 only on V1 prime, and V2 prime, you can actually split it up into, move R0 prime over that, R1 prime, and then so on. But doing it in this particular order among the 3 orders possible will also give you another advantage, in that you see there is also another thing. So R0 is dependent only on V0, okay? And R1 is on among the unprimed set of unprimed variables. R1 is dependent only on, is dependent on more number of unprimed variables. Although you're not eliminating the unprimed variables, but still, this will be, hopefully smaller. Okay, the BDD for this will be smaller. So we eliminate this, and after that you do the conjunction of this and eliminate. Okay, so the idea is you analyze the primed variable dependency of individual functions on the primed variables, and then try to figure out an order in which you could nest the quantifiers, and also look at the dependency of each of the individual component transition relations, how they are dependent, which of the unprimed variables are dependent, and you can delay that. Okay, do things that have fewer dependency on the unprimed variables first. Okay, so so you can play with the order in which you choose the individual components to eliminate. Okay, the variables over. Okay. Yeah. So how do you do this thing? That's what I want to spend. Yeah. Any questions here? So this is the motivation thing. So how do you, So I have. some slides. I go back to this. Yeah, so this is clear. This is somewhat clear now. So you are, what I'm doing is by figuring out, So in general, so this is the example that I chose, okay, to motivate the, the order which you want to do. So in general, what you have is something like this. So you have a conjunction of transition relation with maybe an initial condition, which is dependent on the next one. So, and then if you can get for each of these component transition relation, the set of variables, di, the set of variables that ti depends on. That is easy to get, okay, because you can look at the BDD for that, okay? So if a particular variable does not occur in BDD, you know that it is not, then that Boolean function ti is not dependent on that. Okay? Trying to derive a suitable permutation of these transition functions, which represent the order in which you do to eliminate that, is, so you have to find a permutation such that, a permutation of these things such that T rho I does not depend on and does not depend on any variable in the permutation of J, such that J is greater than or equal to, then you can actually do it in this order. Okay, so if you can kind of order these DIs in such a way that find a permutation such that it preserves this, the DIs corresponding to T, then that suggests you a way, an optimal ordering in which you can eliminate the quantifiers over these TIs for conjunction. Okay, so that's how you will have to do. So the real question is there always such a permuted ordering? If so, how can you get it? And the idea is use information about the set of variables di and ti and things. So it is not, see, to do this, you will see, to get the most optimal ordering, you will have to look at all permutations, okay? And then check if this condition holds good. Therefore, that itself is quite expensive because we're looking at all permutations is quite expensive. But there are some heuristics, cost metrics that you can actually define to over this, once you get the dependency sets, you can define some cost metrics on eliminating these particular variables depending upon the D and the transition relations that are dependent on and get some heuristics. So that I will do, but I will show you an example of where you will get an idea of how, what the most optimal ordering is. Okay. So this is how you can compute. If you given a permutation of indices, then you compute the set of variables, a subset of variables, or the original set, to eliminate it in that order. Okay. So, for example, these the dependencies of T1, T2, T3, or something like this, as I've shown here on the left side. For each of the permutation, I've given you the most optimal. Yeah, this is the most optimal. Okay, the one in the in boldface is the most optimal, because then you can do it in this fashion. First, eliminate X3 from F3. Yeah. So this is how you compute the EIs. Okay, the order in which you eliminate the things. You take for a given permutation, you take row I, okay, which is row 3 here, and then minus take the union of all the things that appear. You subtract the union of all the DIs that appear before it. Okay, so and you end up getting it this way. So, but if you chose a different, I mean, this is the best, most optimal ordering in that it eliminates picks one function at a time to eliminate these variables. Because F3 contains all 3 variables, you eliminate 3 from that, and then you eliminate 2, and then you eliminate F1. And since F1 only contains 1, this is kind of the most optimal ordering. Okay. But if you chose this, you will end up not decomposing it in the finest fashion. So that's the idea. So the question is, how do you get this get this row? Okay. Yes, there are some cost metrics that's actually discussed in the book. I'll go through that. I don't have a slide, for that. That's in the book. Maybe we will revisit this next time. So, but the idea is to compute an optimal ordering that allows you to nest these quantifiers in the most optimal fashion so that you can do it in a certain ordering so that you can eliminate individual variables or some subset of the variables in a certain order, so that at each time when you eliminate the variable, you will get a smaller one than when you eliminate the previous time. That is the idea here. Okay. Yeah. So, any questions? Yeah, but still, I have not given you an. It is hard to get an algorithm that can, hard in the sense of complexity wise, to figure out the most optimal ordering that you can do that, for which you will have to do, in the worst case, look at all permutations. But there are other ways to do it by heuristics to do it. Okay? So that is the takeaway that I want you to have from that. But the thing that you have to realize is that you can, in order to figure out the optimal ordering, you will have to analyze the dependency of the individual transition function, dependency on the variables that the individual transition relations are that depend on. Okay, that's the one that point that I wanted to make. Okay. Okay, so if you don't have any questions, Okay. I'll have to give some time to think. So I'll only discuss, yeah, any questions? Okay. If not, what I want to do is go to this one. Okay. Yeah. So Zubin will, see, I'm going to be one of the, assignment 2 will have a programming part and some small exercises, which will all, the small exercises, written exercises, will be to help you get warmed up on LTL, CTL, and the various other things that I've done. So those are the kinds of questions that I plan to ask you in the small quiz that I might give you. Okay. The programming assignment is, as I've told you, is on implementing the CTL model checker using BDD, specifically the CUDDD package. Okay, now that is, I want you to get started on that. And the first step towards that is for you to get acquainted with the BDD package, which is what I will have Zubin give you a very brief demo of. But I want to give you a small introduction, because that the CUDDD package uses slightly different variant of BDD called zero arc BDD. Now, as far as you're concerned, you'll be using CUDDD package as a black box. It provides a lot of these functions as part of these libraries, okay? We've been talking about these functions: apply, restrict, existential quantification, elimination, and so on. So given BDDs, it has a whole bunch of functions that you can actually use. But I'm getting into the internals of some of these things, just so you will understand what is going on in that. So but this zero arc BDD also, it's strictly not necessary for you to know the details about it if you want to use this CUDD package just as a black box. But still, it is interesting. This gives exponentially more compactness than standard BDD. So it is interesting and informative, instructive for you to know. And that's why I'm taking 5 minutes to cover this. And after that, Zubin is going to take about 10 minutes to introduce you to CUDD. So stick around, please. Okay? So the zero arc BDD, it has only one type of leaf node, one. So normally in standard BDD, you have one as well as zero. Okay. And I'll show you an example. There is a limitation of having ones and zero, okay, both 1 and 0 as a leaf node. See, I mean, the portion of a BDD that takes that function to 1 is the one for which the function evaluates to 1, okay? And all the paths that take you to 0 are the ones that go to evaluate to 0. The result of this thing is, if you have a Boolean function f and a negation of that function, obviously there cannot be any sharing, very little sharing between the two, because they do, the f will take one set of assignments to 0, whereas f bar takes the other set of assignments to 0 and vice versa. Okay, so that's why. So the idea behind this is this zero arc BDD is to use only one type of leaf node. So you simultaneously represent, which helps you to represent both f and f bar by sharing nodes almost completely between those two function and its negation function. So that is the idea behind it. The result, you get more degree of sharing. Okay, so each node, but it only has one kind of leaf node 1, but each node has a one edge and either a regular zero edge, the standard zero edge, or a special kind of edge called a complemented zero edge, denoted by a dash line with a bubble. That's what I'm using. So, and this thing is called complemented edge. That means that the function is when that leads to 1, when such an edge, you follow such an edge to 1, you have to treat it as 0 value instead of 1 value. The other thing is every BDD is augmented with a root node, which is connected to the unrooted BDD, which has these edges with a single one edge or a complemented 0 edge. Okay? And the way you evaluate such a BDD is the result of a function for a path is read as 1 if and only if the number of complemented 0 edge in the path is even. If it is odd, you will read it as 0. Okay? So these are the rules for a zero arc BDD. So here is an example. Let's see. As I said, in the standard BDD, a 1 node is represented like this with 1 and a 0 as 0. As I said, the first rule is in zero arc BDD, you do not have, you only have 0 and 1. So, I mean, you only have 1. Therefore, what you do is you only have 1. And then, as I said, there is a root node, okay, from which there is a solid edge going to 1, which means this part represents the constant function 1, okay? The other part represents the constant function 0, okay? Why? Because if you follow from the root node to 1, you're following an odd number of you're tracing an odd number of complemented arc edge. Okay, and therefore, when you go from this to this one, you should treat it as 0. Okay, so that's the convention. Yeah. So this is how it represents. That's how you will see. So all your BDDs will be representing both the positive part, I mean, and the function and its complementation at every level. That's how it will be doing. So if it's x, it is x1, x0. I mean, this is how x is represented in standard. And x naught, the x bar is represented like this. Okay. So this is where you see. So you cannot have, there can be no merge between these two things. Okay, they'll have to be separate. Whereas here, what you do is you find to see something in the share. So x, if it is 1, it if it goes to 1, and then if x is 0, then you go use a complemented arc edge and make it go to 1, and then you have at the root you have a solid bar. Okay, so this part here on the left side, starting from the root node x, represents the function f of x is equal to x. Okay, so x bar, you have to put another complemented arc edge. And if you notice that here, when you follow the one edge here, it'll have odd number of 0 arc, and therefore it will be read as 0. And when you trace the 0 part, okay, then you will have even number of 0 arc edge, and therefore it will be 0, and so on. Okay, so that is how it is it's represented. So similarly here you see you have x and y bar, and x, the complement of that, x bar and y. Okay, and here in standard BDDs you cannot have any sharing between them, and this can be represented. Both these functions can then be represented using much smaller BDD. So a 0 arc BDD. So you will get the thing of representing both f and f bar. Whether you use it or not, you will get f bar for free. Okay, so that's what the thing is. So there are several, yes, okay, and here are more examples that I've seen. So some interesting exercises I might put on the written assignment. How do you convert a standard BDD to a complemented arc BDD, and how do you do all the operations of complemented arc BDD? Okay, so this is a bit of a rushing, but so, and I don't think there is, if you start doing it by hand, try a few examples out, you will get the hang of it. Okay, and at a later time, maybe we can discuss some of these interesting problems. Okay, but one thing to note is that you get a very big, especially in those kinds of functions. See here, what it does is you're taking the kind of sub part which uses the negation of another part. Okay, in somewhere down the line, then you can't have much sharing in this notation. So here, with an extra edge, you get significantly more sharing. Okay, so sorry, yeah, I'm already in 4:45. So yeah, stick around, please. So there are 10 minutes. So zoom in.
What is the reference for material covered today?
Yeah, the 0 arc. No. All the partition transition relations I already gave you the reference. Okay, it's in the book. The book chapter. There is book chapter 8.
Okay, in chapter 8.
Yeah, 8.6.1. Okay, look at chapter 8, partition transition relation. Now, this 0 arc BDD example, I don't know if that is not discussed in the book. Okay, I'm introducing that because you should not get startled when you see that in CUDD, because CUDD uses the 0 arc BDD. Okay, and I think a lot of the state-of-the-art BDD packages use this kind of thing because this is much more compact. But of course, in CUDD package, there is a utility. When you print it, it will convert, at least for printing purposes, a 0 arc representation into a standard BDD. So you can read all the stuff that it creates by using this print notation. So technically for doing it, you don't need to, but I encourage you to understand this one. Now, I don't know where this thing is described. I mean, I'm sorry to say that there is no, maybe one of those things. I mean, I'll find out, okay? So I don't remember where I got it. I think I educated myself about the zero arc BDD by experimentation and then doing the thing. Yeah. So those are the only two parts that I had here. The other part is all, the rest of the BDD part is discussed in the book. Yeah. Okay, Zubin, take away.
Okay, I can't share my screen.
Yes, yes.
Okay, you can see my screen, right?
Yes, I can see it. I hope the rest
Okay.
can.
So, COTD is a C library for
Oh, I don't know. Maybe it's okay for the younger eyes that
yeah,
the rest of you
yeah.
are.
So COTD is a C library for creating and manipulating BDDs. So because it's a C library, there's a lot of tedious memory management and things that you have to do when you're using it. So yeah, the installation instructions are also a bit complicated, but I'll leave up some instructions on Moodle. But the way it works is that uh, yeah, so you hash include CUDD in your C program, and
Is there CUDD library for Python?
I'm not sure about Python, but there are bindings for Haskell, and there should be for Python and other languages also. So that can make this easier. But CODD itself is only a C library, but you have to use external bindings. So if you want to use it with any other language. So once you install the CODD library, you will need to, uh, when compiling your C program, you'll need to link it in with lcodd. If I do that, and then so what this program does is it initializes CODD, then it creates a new variable, then it increases the reference count of that variable because this is C memory management stuff, because C does not have a garbage collector, so you have to manually track which nodes in the BDD graph are still alive and should not be destroyed. Uh, and then we simply in the last few lines just display the BDD. So if I run this, it shows that I have just one variable and it shows some statistics about that. Uh, it has also uh, made a graph for this single variable BDD, and this is it's written that out too. So if you want to do more complicated things, you can do it in C, but it would be easier if you do it in a more high level language which has CUDD bindings. So Haskell has CUDD bindings, so you can. Uh, so I'll close the C program now, and this is the same. This is a Haskell program. It creates four variables, 0, 1, 2, 3, and it takes it does and v3 v4 and v1 v2 and ORs these things together and then prints them out. So it's so this bit is v1 and v2 or v3 and v4. This is the BDD that we are constructing, and this again writes out the graph as a dot file. So we can run this program. Yeah, we saved it here. So this is what uh, the BDD that it generated would look like. So it's taking the AND of these two variables. So if both of these are true, or if both of these are true, it results in a 1. Otherwise, it results in a 0.
This is standard BDD. Right?
This is the standard BDD notation. It's so by default. So I'm converting it to something called ADD. If you just try to dump out the BDD produced by the OR of the ANDs, uh, then you'll get uh, in the complemented arc notation uh, that was just described. So you have uh, dotted lines, which are the regular else edges, and the dashed lines on top. Sorry,
No, it's the
yeah,
reverse. No?
no, the dashed lines are the
Complemented.
complement. Yeah,
Okay.
so these are the complemented lines. So yeah,
Yeah, see, that's why. Yeah. So this is the root node. It shows a root node also. Okay. I mean, it shows a root node everywhere.
yeah.
But here, that can be either a solid edge or a complemented edge, depending upon whether that is representing the F
So
naught.
Sir, I did
so
not.
this entire function.
I,
So this later part is negated. So uh,
sir,
Yeah.
I did not quite understand the meaning of complemented edge. Could you describe it again?
Yeah, the complemented edge okay.
okay, I think so the dotted edge is the complemented edge. Sorry,
That's
so
what
the
I thought.
yeah.
Yeah, the dashed edge is the regular edge. So the dotted edge, I mean, the complemented edge here is the dotted, not the dashed. Okay. So the way you should read it is, okay, how do you understand a BDD, the function? So you trace. So you just trace the path from the root. In the standard case, you trace the path from the root to a leaf. Okay. And if it is a 1, then no, yeah, just keep it that. Yeah. So here, so you count, the number of, as you trace down from that path, because there's only one kind of leaf edge here, one. So every path leads to 1. So how do you check if you get a 0? You count as you go down the path. Count the number of times that number of occurrences of.
What exactly a complemented edge means actually?
Well,
That means the function below that is negated. So if
negated.
there was a
That's what it means.
whole tree below that, it points to the
Uh,
negation of that tree.
Suppose we are at the 0th level, then we decide upon that variable whether it to set it to
So
1 or
I'll
0.
show you 1 second.
Now, but before you do that, okay, yes, that what Zubin said was exactly correct. But the result of that thing is when you trace it, you need to count the number of times, number of occurrences, number of times complemented edge occurs. If it
I
is odd,
haven't understood the concept of complemented edge. Means,
okay.
see, we have to
Yeah.
make a decision, right? If we
So
set
look,
variable
if
to,
I
we take the uh, regular edge, and if it is 0, we take the dotted edge, and when we take the dashed edge.
we take the dashed edge when it is a 0, and we complement the rest of the function. So look at this. So this is the root node. Originally, from the root node we have a solid edge, but if we uh, add a knot around the entire function, if we add a knot around the entire thing, and then generate it, then this edge turns into a complement edge. So it represents the negation of this entire
Yeah,
tree.
that is one.
Yeah.
But if you want to understand the thing, just trace it down. Okay. So
So
if you go from
if you
F
go down a complement edge, the eventual result you get is the negation of
no. That is
the
not as
actual
simple.
thing.
It is the number of whether it is odd or even. Okay.
Yeah, so I mean, every time you go down a complement edge, you have to
Yeah,
remember to
but then you
negate.
don't know until you reach that one,
Yeah.
whether the thing or not. So either you have to figure out what the function at each node is and then take the complementation. But if you just want the value of this function for a particular assignment, then what you do is, let me see. So this is solid edge. So when I do this, okay, this is 0, 0. So now there are two, uh, you know, even number of occurrences of complemented thing. Okay. Therefore, I should read that for 0, 0, this is 1. Okay. As opposed to this 0, 1, 1. Okay. And for 0, 1, 1, although you're going to 1, you have encountered the complemented edge only once.
So
Therefore, you
complemented edge is 0 only in
Yeah, it's always 0. Yeah.
okay.
complemented edge is always 0 the value. So there are two kinds of 0 edges.
So we
One is
substitute
complemented
0 in
edge.
the formula and complement it.
Yeah.
Correct.
Okay, okay.
Yeah, there are two kinds of 0 edge. One is complemented, one is standard. Okay. So the complemented edge means when so you should take the negation of it, okay, the result. But
So
if you get even number, you will end up, you end up canceling. Yes.
so it allows us to do this kind of sharing. So right now we have just AND v3 v4, and this is connected to this via dashed lines, which is the regular edge. But if we add a knot around this, we'll see that the structure remains the same, just the edge becomes different. So this portion of the graph can be of the BDD can be shared by some other function, and it doesn't have to change. Only the incoming edges change. So it allows us to save on uh, exponentially many nodes in the graph. So you see, if I wrapped this and in a knot, then we got this edge turned into a complement edge, these two edges. I think that is it for now. I'll upload instructions on how to install and use CODD on Moodle.
Yeah, I'll put out the second assignment in two parts. One is I will put out the programming assignment, okay, first, because I would want you to get started on it. The other written assignments is more for you to warm up on all the concepts that we have covered so far, so you won't forget, okay? So just to keep you honest in things. So consider it as a learning experience for you by working out those examples. Okay. And hopefully that will prepare you for the small quiz that I will have later.
So for the programming part of the assignment, we will be using the CBUDD package.
Correct. Correct. And I will give you exactly the things. Basically, we'll be implementing all the fixed point algorithms for all the operators. Okay.
Yeah.
Using BDDs. So
Right.
where,
So I mean, we can do that in C, right?
yeah, I'm okay with any language. Okay. But Zubin had a warning for people wanting to do it in C. For some reason, you said he preferred the Haskell interface was better. I don't know why. You may want to explain.
So, like I explained in C, you have to do a lot of manual memory management, and it becomes very. So, look at this one. So, this one is not that bad, but
Are you sharing your screen?
oh, 1 second. Uh, yeah. Mm, Uh, yeah. So, if you look at all the, sorry. So you have to do a lot of manual memory management and free stuff, and you can get use out of free others. And it becomes very tedious to do it in C because you have to do all this setup code and
Why do you have to do the memory management? Ah, I see. So, so you have to allocate appropriate number of nodes. And
yeah, and you have to maintain references to them and dereference them when you're not using them anymore, and free the whatever things you've allocated and things like that. So it becomes pretty tedious if you get too large programs. So it's your choice, but you can do it in Python, you can do it in Haskell.
yeah, but I think if we could get some information that can help them for Python. Okay, you already know Haskell.
Yeah,
You know how
yeah.
many. There are probably some set of people that may want to do Python.
It looks like there's a Python library called DD which can use CODD also as a backend. So it is more general. It allows for any kind of it is a BDD library in Python, but it can use a CODD backend. So it can use other backends also. It's like SMTlib and Z3, but that looks to be maintained. The other library I was seeing didn't seem to be maintained in Python. So this one seems to be DD. It's called yeah, just DD, binary decision diagrams in Python.
So we have everything uploaded on Moodle, correct? So all the
Uh,
documents, link.
uh, for this, no, not yet. I'll upload it today.
You have to do it quickly so that they can
Yeah. Okay.
start with this. Yeah. By the way, the book, discusses both chapters 8 and thing, especially chapter 8, discusses in detail how you can implement using BDD package. So that should be of great help uh, for you as a reference for doing the implementation. I'm just thinking of, whether I should want you to do some optimization, such as this partition transition relation or not. That I will make a decision on. Yeah? So there will
Does
be.
UDD have a C++? I'm sorry.
Go ahead.
So does UDD have a C++ wrapper or something like that?
I think there might be a C++
Hello?
wrapper also.
Yeah, that might be easier.
Yeah.
Okay. Any other questions?